Have you ever wondered what it might be like to experience time in reverse? To watch a shattered glass leap back into your hand or see rain rise from the ground into the clouds? It sounds like pure science fiction, but what if I told you that some of the brightest minds in physics are seriously exploring the possibility that time could actually run backward? Not here, not in our familiar universe, but perhaps in another. This isn't just wild speculation. It's a question that gets to the very heart of how we understand reality, and it all revolves around a deceptively simple idea known as CPT symmetry. CPT symmetry stands for charge parity and time reversal symmetry, and it's one of those foundational principles in physics that sounds complex but opens up a universe of breathtaking possibilities. At its core, this concept suggests that if you take our universe and flip the charge of every particle, mirror its spatial dimensions, and reverse the flow of time, the laws of physics should still hold true. In other words, there could exist a kind of mirror image of our cosmos, an alternate reality where antimatter takes the place of matter, left becomes right, and time itself flows backward. Imagine a world where cause and effect operate in reverse, where the future influences the past, and the arrow of time points in the complete opposite direction. In this video, we're going to journey to the frontiers of modern physics to explore whether such a universe could truly exist. We'll dive into the strange and counterintuitive realms of quantum mechanics and cosmology, where particles behave in ways that defy common sense, and where the very fabric of spacetime might hold secrets we're only beginning to uncover. Along the way, we'll meet some revolutionary ideas that challenge everything we thought we knew about time, existence, and the nature of reality itself. So settle in and open your mind, because by the end of this exploration, you may never look at the universe the same way again. To truly grasp why this idea is so revolutionary, let's break down each component of C, P, and T, starting with charge. Flipping the charge of every particle essentially means swapping matter for its opposite, antimatter. For every electron with a negative charge, there's a positron with a positive charge. In our universe, when matter and antimatter meet, they annihilate in a burst of energy. But in this hypothetical mirror reality, we're not just swapping a few particles, we're redefining the entire cosmos. Antimatter would be the default building block of everything: stars, planets, even life itself. It's a universe constructed from the very substance we usually only see for fleeting moments in particle accelerators. Next comes parity inversion, or the P symmetry. This is the concept of creating a perfect mirror image of the entire universe. In this mirrored state, everything that was left-handed becomes right-handed and vice versa. For a long time, physicists believed the laws of nature were perfectly symmetrical, that a mirror universe would behave exactly like our own. But in the 1950s, a groundbreaking experiment by Qin-Sheng Wu revealed something astounding. She observed that the weak nuclear force, which is responsible for radioactive decay, actually violates this parity symmetry. In other words, the universe on its own has a slight but fundamental preference for left-handedness. A process that works one way in our world might not work at all in its mirror image if only the parity is flipped. Then we have the reversal of time, the T symmetry. This is the most mind-bending part of the trio. At the level of individual particles and their interactions, the laws of physics don't seem to care which way time is flowing. If you were to film two particles colliding and then play the recording backward, the reversed event would still obey all the same physical rules. It would look just as valid and natural. This is true for the fundamental forces like electromagnetism and gravity. However, when we zoom out to our everyday world, this symmetry completely falls apart. We never see smoke gathering back into a cigarette or an ice cube reforming in a warm glass. This is because of the second law of thermodynamics, which introduces the arrow of time through the concept of entropy, the universe's tendency toward disorder. While the microscopic laws are time-symmetric, the macroscopic world is not. This is where CPT symmetry becomes so powerful and necessary. Individually, we've seen that C, P, and even T symmetry can be violated. But here's the incredible part. Physics believes that if you apply all three transformations together, flipping charge, mirroring space, and reversing time simultaneously, the combined symmetry must always be preserved. This is a cornerstone of quantum field theory. It means that while a universe with only time running backward might not be possible, a universe that is the full CPT mirror of our own must be a valid possibility according to the fundamental laws. It would be a cosmos where antimatter is dominant, left and right are swapped, and the arrow of time points in the opposite direction, yet it would be every bit as real and physically consistent as our own. So let's take a moment to really visualize what each of these three transformations would mean on a cosmic scale, starting with charge conjugation. This is the process of swapping every single particle in the universe with its corresponding antiparticle. Imagine an electron with its familiar negative charge instantly transforming into a positron, its positive charge twin. A proton would become an antiproton. In this new reality, the very stuff that makes up everything, you, me, the screen you're watching this on, would be composed entirely of antimatter. We often think of antimatter as this exotic, volatile substance that annihilates on contact with matter, but in a charge-conjugated universe, it would be the normal, stable state of existence. Stars would burn with antimatter fusion, and chemistry would work exactly the same way, just with all the charges flipped. Next, we apply parity inversion. This is like holding up a perfect, universe-sized mirror to our reality. Every spatial coordinate is flipped. What was on the left is now on the right. A galaxy spinning clockwise would now spin counterclockwise. Even the very concept of handedness in molecules would be reversed. For most of the forces we know, like gravity and electromagnetism, this mirror world would be indistinguishable from our own. The shocking discovery, however, was that this isn't universally true. The weak nuclear force which governs things like radioactive decay actually violates this parity symmetry on its own. This means a process that relies on the weak force might look completely different in the mirror. A left-handed neutrino might only interact one way, but its mirrored, right-handed version might not interact at all. So a universe with only its parity flipped would actually operate under slightly different rules. Then we come to the most perplexing transformation, time reversal. This isn't just running a film backward, it's the literal reversal of the sequence of every single event. At the most fundamental level of particle physics, this symmetry largely holds. The equations that describe how particles collide and scatter work just as well whether time is flowing forward or backward, but our macroscopic experience screams otherwise. We never see a broken egg reassemble itself on the floor and leap back into our hand. This paradox is explained by the second law of thermodynamics and the inevitable increase of entropy or disorder. While the microscopic laws might be blind to the direction of time, the overall system of the universe is not. A universe with only time running backward would be overflowing with what we would perceive as miraculous events. Disorder spontaneously organizing itself into order, heat flowing from cold objects to hot ones. It would appear to be a world of impossible magic. This is where the true elegance of physics reveals itself. Individually, each of these symmetries can be broken. We've seen the weak force violate parity. Certain particle decays show evidence of charge parity violation, and time's arrow seems irrevocably forward. But the profound and beautiful principle of CPT theorem states that if you apply all three transformations together, swapping every particle for its antiparticle, mirroring the entire cosmos, and reversing the flow of time, the resulting universe must be perfectly indistinguishable from our own according to the fundamental laws. The combined CPT symmetry is believed to be absolute. The individual violations cancel each other out. the slight preference for left-handedness in our weak force interactions would be perfectly balanced by the fact that in this CPT-transformed universe, you're also dealing with antimatter and time flowing the other way. It's this complete package that allows physicists to seriously entertain the idea of a genuine mirror cosmos, a universe where time runs backward, not as a flawed copy, but as a perfect, lawful counterpart to our own existence. This profound belief in CPT symmetry isn't just a passing fancy for physicists. It's a conviction rooted in the most robust mathematical framework we have for describing reality, quantum field theory. The story behind this is as compelling as the concept itself. It begins with a brilliant mind, Wolfgang Pauli, and what's now known as the CPT theorem. This theorem isn't a mere suggestion or a hypothesis, it's a fundamental proof. Pauli demonstrated that for any quantum field theory that respects the core principles of special relativity, specifically Lorentz invariance, the combined symmetry of CPT must be absolutely preserved. This means that if your theory correctly describes particles and forces in a way that's consistent with Einstein's relativity, then it must obey CPT symmetry. There's no way around it. It's not an optional feature. It's built directly into the bedrock of the universe's operating system. This gives CPT symmetry a status that very few principles in physics enjoy. It's not something we merely observe to be true so far. It's something we expect to be true always, because the entire theoretical structure of modern particle physics would come crashing down without it. If an experiment were to ever find a definitive violation of CPT symmetry, it would send theorists back to the drawing board in a monumental way, forcing a complete overhaul of quantum field theory and our understanding of relativity itself. That's how central this idea is, and the experimental evidence overwhelmingly supports this unshakable theoretical foundation. Physicists have put CPT symmetry to the test with incredible precision, and it has passed every single challenge. Consider the comparison between particles and their antiparticle counterparts. We can create and study antihydrogen atoms in laboratories which consist of an antiproton and a positron. The most precise measurements show that the mass, charge, and magnetic moment of a proton and an antiproton are identical to an astonishing degree. Any tiny difference would hint at a CPT violation, but no such difference has ever been found. The energy levels in hydrogen and antihydrogen are the same. If they weren't, if an antiproton behaved differently from a proton in any fundamental way, it would break the symmetry. But the universe, as far as we can measure, plays by these perfectly symmetrical rules. This incredible resilience is why CPT symmetry is considered one of the most sacred principles in all of physics. It connects the worlds of the very small, described by quantum mechanics, with the world of high speeds and vast distances, described by relativity. It acts as a guiding light, a non-negotiable rule that any new theory, whether it's string theory or loop quantum gravity, must ultimately adhere to. So when we talk about a universe where time runs backward, we're not engaging in frivolous speculation. We are following the implications of one of the most rigorously tested and mathematically sound concepts in existence, a principle that allows us to confidently explore the idea of a true cosmic mirror. This elegant symmetry in the laws of motion is one of the most fundamental and surprising features of our universe. If you were to film a perfect pendulum swinging back and forth in a vacuum with no air resistance to slow it down, and then play that recording backward, you would be completely unable to tell which version was the original. Every action, every transfer of energy would look just as valid and natural in reverse. The same is true for a single planet orbiting a star in the emptiness of space. The mathematics that describe its elliptical path, governed by gravity, are perfectly reversible. The equations work with the same flawless precision whether the variable for time is positive or negative. There is no built-in arrow. This idea extends to nearly every corner of classical physics. The famous laws of motion laid out by Isaac Newton in the 17th century show no inherent preference for the future over the past. Force equals mass times acceleration. This principle holds true regardless of the direction time is flowing. If a billiard ball strikes another, causing it to roll away, the event in reverse, a ball rolling in to strike another and stop, is just as physically sound. The laws governing the collision are indifferent to the sequence. This presents us with a profound and puzzling contradiction. Our daily experience screams that time has a definite direction. We remember the past, we anticipate the future, and we witness irreversible processes everywhere. Ice melts in a warm room, a drop of dye disperses in a glass of water, a log burns into ash. These events never spontaneously reverse themselves, yet the underlying mechanical laws that should explain these very events are completely blind to this flow. The fundamental rules seem to describe a universe that is, at its heart, ambivalent about time's arrow, while the world those rules create is absolutely certain about it. This is the central mystery that forces us to look beyond the pristine equations of mechanics and into the realm of probability and disorder to find the true source of time's direction. So if the fundamental laws are so perfectly symmetric, why does our reality feel so stubbornly one way? This is the core of the arrow of time problem, the deep and puzzling gap between the laws that govern the particles and the undeniable forward rush of our everyday experience. We don't just observe time passing, we are carried along by it, building memories of a fixed past and facing an open, uncertain future. A cup shatters on the floor, and we know with absolute certainty that those pieces will not spontaneously fly back together. This intuitive understanding of cause always preceding effect is so deeply ingrained in us that we rarely stop to consider how bizarre it is that the universe's rulebook seems to ignore it entirely. The key that unlocks this paradox is a concept that originated not in the grand physics of relativity, but in the more practical world of 19th century engineering, entropy. Coined by Rudolf Clausius, entropy is a measure of disorder or randomness in a system. The second law of thermodynamics states that the total entropy of an isolated system can never decrease over time. It can only stay the same or increase. Think of it this way: your desk might start the day neatly organized, but as you work, papers scatter, pens roll away, and coffee cups multiply. It takes effort and energy to clean it, to impose order again. Left to its own devices, any system will naturally trend toward a state of higher disorder. This is the thermodynamic arrow of time, and it gives our universe its relentless forward thrust. We see this play out in countless ways. A drop of ink diffuses in a glass of water, spreading out until the entire liquid is a uniform light shade. We never see that ink spontaneously gather back into a single, dense droplet. A hot cup of coffee left on a counter will gradually cool to room temperature as its heat energy disperses into the air. It will never draw heat from the cooler room to make itself hotter again. These processes are irreversible because they involve an enormous increase in the number of ways the particles, the ink molecules, or the heat energy can be arranged. There is only one way for the ink to be in a tight droplet, but a near infinite number of ways for it to be spread evenly throughout the water. The system naturally gravitates toward the state of highest probability, which is the state of maximum disorder. This explains why we never see the broken egg reassemble. The shattered shell and the spilled yolk represent a state of far higher entropy than the intact egg. For all those pieces to precisely reverse their trajectories, coordinate their movements, and leap back into the shell would require them to find the one in a trillion path back to a state of perfect order, a statistical near impossibility. Our brains themselves are part of this process. The formation of memories is a physical, chemical event in our neurons that also increases entropy. We remember the past because it is the state of lower entropy that led to our current, higher entropy state of knowledge. The future, by contrast, holds a vast array of possible disordered states, and we cannot remember it because it hasn't happened yet. The increase of entropy provides the directionality that the fundamental laws lack, creating the irreversible flow we all experience. It is the reason time has an arrow and not just a line, but this profound connection between time and disorder only deepens the mystery. If the underlying laws are time-symmetric and the arrow emerges from statistics, we are left with a monumental question. Why did our universe begin in such an extraordinarily ordered state? The entire concept of entropy increasing requires a starting point of exceptionally low entropy. Think of it like a deck of cards. A brand new deck comes perfectly sorted by suit and number, a state of very low entropy. If you shuffle it, you naturally increase its disorder, but we would never expect a randomly shuffled deck to spontaneously sort itself. Our observable universe is that perfectly sorted deck from the moment of the Big Bang, a state of almost unimaginably low entropy that has been unraveling and becoming more disordered ever since. This is the ultimate source of the arrow we all experience, and its origin is one of the greatest puzzles in all of cosmology. What makes this initial condition so special is its staggering improbability. For the universe to have begun with such perfect order, the initial configuration of all matter and energy must have been exquisitely precise. The laws of physics don't dictate this. They would have been just as happy with a messy, high-entropy beginning. So why did ours start this way? Some physicists like Sean Carroll suggest we might be part of a much larger multiverse. In this view, our Big Bang was just one event in a vast cosmic landscape. In an infinite multiverse, even the most improbable events must happen somewhere. We find ourselves in a region that began with low entropy not because it's likely, but because such a beginning is a prerequisite for the formation of galaxies, stars, planets, and ultimately, life forms like us who can ponder the question. This is known as the anthropic principle. We observe a clear arrow of time because we are the product of it. Other theories look to the nature of gravity itself. In the early, incredibly dense universe, gravity was the dominant force. While the dispersal of particles increases entropy, the clustering of matter under gravity also represents a form of increasing disorder. A perfectly smooth, uniform distribution of matter has lower gravitational entropy than one with clumps, clusters, and black holes. A black hole is actually one of the highest entropy objects possible. So the arrow of time might be inextricably linked to gravity's relentless pull, driving the universe from a smooth beginning toward a clumpy, structured, and ultimately disordered end. This gravitational tension between order and disorder adds another layer of complexity to our understanding of why time flows in one irrevocable direction. So how do we know that this foundational symmetry isn't just a beautiful mathematical idea, but a true description of reality? The answer lies in some of the most precise and painstaking experiments ever conducted. To test CPT symmetry, physicists don't need to find a mirror universe. They can create the crucial components of one right here in the lab. By producing and studying antimatter particles with unimaginable accuracy, they can compare their fundamental properties to those of their matter counterparts. If CPT symmetry holds, these properties must be absolutely identical. Any tiny, measurable difference would be like finding a crack in the cosmic mirror, a sign that the symmetry is broken. The most compelling evidence comes from the breathtakingly precise comparison of particles and their anti-twins. Take the electron and the positron, for example. These are not just opposites in charge. For the universe to be CPT symmetric, they must be perfect mirror images in every other way imaginable. Their masses have to be exactly the same. Their intrinsic spin and magnetic characteristics must be identical. Even their lifetimes, how long they exist before decaying into other particles, must match perfectly. Researchers have measured these properties to an almost unbelievable degree of certainty. The mass of an electron and a positron are the same two within less than 1 part in a billion. Their electric charges are equal and opposite to a similar, extraordinary precision. But the true crown jewel of these experiments involves measuring something called the magnetic moment. Think of this as the strength of a particle's tiny internal magnet. For an electron or a positron, this is a fundamental fingerprint. The standard model of particle physics makes a very specific prediction for what this value should be. Using ingenious devices called penning traps, which use electric and magnetic fields to suspend a single particle in a perfect vacuum, scientists can observe one electron or one positron for extended periods, measuring the delicate ways it wobbles and precesses. The result, the magnetic moments of the electron and positron have been shown to agree with each other, and with the theoretical prediction to better than 1 part in a trillion. That's a level of precision equivalent to measuring the distance from New York to Los Angeles with an error no wider than a single human hair. Other tests provide equally strong support. Physicists have created entire atoms of antimatter, like antihydrogen and antiproton orbited by a positron, and compared their energy levels and behaviors to regular hydrogen. So far, within the incredible sensitivity of our instruments, light emitted and absorbed by antihydrogen has exactly the same properties. It behaves in every way as a perfect mirror image. These aren't just simple measurements, they are monumental achievements in experimental physics, and they all point to the same inescapable conclusion. As far as we can tell, CPT symmetry is flawless. The cosmic mirror remains unbroken, giving us immense confidence that a universe operating under these reversed laws would indeed be a valid and physically consistent reality. Now let's use that foundation to truly stretch our imaginations and picture the reality of such a place. A universe transformed by full CPT symmetry would be far more than a simple reflection. It would be a perfectly valid, self-consistent cosmos operating under the exact same physical laws as our own, but with every single one of its fundamental properties inverted. It is our universe's ultimate twin, separated not by space, but by the very definitions of charge, handedness, and time. Envision a realm where the arrow of time points in the opposite direction. From our perspective, looking into this mirror cosmos, events would unfold in reverse. But for an observer living within that universe, their experience would feel entirely normal. They would have memories of what we would call their future, and they would anticipate what we see as their past. A tree would grow from a fully formed canopy down into a seed buried in the ground. A civilization might watch as their cities meticulously deconstruct themselves over centuries, returning building materials to pristine quarries and forests. To them, this would not be strange. It would simply be the natural, logical flow of cause and effect, with their consciousness perfectly aligned to this backward progression. The very substance of this reality would be utterly foreign to us. Antimatter would be the default state of all things. Stars would shine by the fusion of anti-hydrogen into anti-helium. Planets would form from rocks made of anti-silicon and anti-oxygen. Life, if it arose, would be built from complex anti-organic molecules. An anti-person standing on an anti-planet would look up at an anti-star in the sky and perceive it as completely normal matter. If we were somehow able to visit, our mere presence would be catastrophically volatile, as every particle in our bodies would seek to annihilate with its antiparticle counterpart in that world. Even the concept of direction would be flipped. This is the parity transformation. A galaxy that spins clockwise in our universe would spin counterclockwise there. The DNA helix of any potential life form would twist in the opposite direction. The subtle asymmetries we see in our weak nuclear force interactions would be mirrored, perfectly balancing out to preserve the overall law. A left-handed neutrino in our world would manifest as a right-handed anti-neutrino in theirs. Every single spatial coordinate is inverted, creating a cosmos that is the precise mirror image of our own in every dimension. The most profound takeaway is that this CPT mirror universe is not a flawed imitation or a broken version of reality. According to the unwavering laws of physics, it is just as real and physically valid as our own. There is no experiment an observer in that universe could perform that would reveal their world to be backwards or wrong. Their physics textbooks would contain the same elegant equations. Their scientists would discover the same fundamental constants. They would gaze out at the cosmos and develop their own theories of a universe that began in a state of low entropy and has been evolving forward in time ever since. Their time completely unaware that from our perspective, their history is our future and their matter is our antimatter. The symmetry is so complete and so powerful that it suggests both perspectives are equally true, forcing us to confront the incredible idea that our own experience of reality might be just one possible viewpoint in a far grander, more symmetric cosmic tapestry. This deep connection between CPT symmetry and the nature of antimatter is perhaps one of the most elegant and mind-bending ideas in all of physics. It suggests that these three transformations aren't just a random checklist. They are intimately intertwined, offering a radical new way to understand what antimatter truly is. The theory posits that an antiparticle isn't merely an opposite charged twin of a particle. It can be interpreted as its ordinary matter counterpart moving backward in time. This revolutionary perspective was most famously championed by the brilliant and unconventional physicist Richard Feynman. He developed a way of looking at particle interactions, now called Feynman diagrams, that beautifully illustrate this concept. In these diagrams, which are like little maps of particle collisions, a particle moving forward in time is represented by a line with an arrow pointing forward. But Feynman realized that a line representing an antiparticle, like a positron, could be mathematically treated as an electron with its arrow of time reversed. It's an electron traveling backward along the time axis. Let's make this abstract idea a bit more concrete. Imagine you see the birth of an electron-positron pair popping into existence. This is a common event in particle accelerators. From one perspective, we see two particles, a negative electron and a positive positron. But from Feynman's time-reversed viewpoint, you could interpret that same event as a single electron that, at a certain point in spacetime, executes a dramatic U-turn in time. It travels backward as a positron for a while, then turns around again to continue forward as an electron. The math works out identically. The positron isn't a separate entity. It's just the electron's path when viewed from a different temporal direction. This isn't just a clever mathematical trick. It provides a profound and simplified explanation for why all the properties of particles and antiparticles must be so perfectly mirrored. Their masses are identical because, in a very real sense, they are the same particle. Their charges are opposite because if you imagine something with a negative charge moving backward in time, its influence on the world around it would appear to us moving forward, exactly like a positive charge moving forward. This time reversal interpretation elegantly explains why the laws of physics demand this perfect symmetry. This perspective also helps demystify one of the great puzzles of our universe, why there is so much more matter than antimatter. If the Big Bang created equal amounts of both, as our theories suggest, why didn't they all annihilate each other, leaving behind a universe of pure energy? The fact that we exist in a material world means some asymmetry must have favored matter. Feynman's idea offers a unique lens for this problem. It suggests that the initial conditions of the universe may have set an overwhelming preference for particles to be moving forward in time, creating the arrow of time we experience and the matter-dominated reality we see around us. In this view, the missing antimatter isn't missing at all. It's a manifestation of the one-way flow of time from the Big Bang onward. Yet for all its proven resilience, the absolute nature of CPT symmetry faces its most intriguing challenges not from within the well-trodden paths of the standard model, but from the wild frontiers of physics that seek to move beyond it. The quest to unify Einstein's theory of gravity with the quantum realm has given rise to some of the most ambitious theories ever conceived, and within their complex mathematical frameworks, the sacred status of CPT is sometimes called into question. These are not proposals that CPT is broken in a simple or obvious way. Rather, they suggest that under the most extreme conditions imaginable, the very fabric of space-time might fray just enough to allow for a tiny, almost imperceptible violation of this most fundamental symmetry. One of the primary arenas for this possibility is the realm of quantum gravity. Our current understanding, based on the flawless marriage of quantum mechanics and special relativity, demands that CPT be preserved. However, when we try to incorporate gravity, the curvature of spacetime itself, into the quantum picture, the mathematics becomes vastly more complex and less certain. Some approaches to quantum gravity introduce inherent discreteness or a fundamental graininess to spacetime at the smallest possible scale, known as the Planck length. In such a framework, the smooth, continuous background that underpins Lorentz invariance, and by extension the CPT theorem, might begin to break down. If the universe has a minimum unit of space or time, it could potentially provide a preferred frame of reference, a subtle anchor that would allow the absolute symmetry of CPT to be ever so slightly compromised. String theory, perhaps the most famous candidate for a theory of everything, also entertains scenarios where CPT might not be perfectly sacred. In certain string theory models, the vacuum of the universe, the underlying ground state of reality, is not unique. Instead, there could be a vast landscape of possible vacua, each with slightly different physical properties and constants. In transitioning between these states, or if our universe exists in a particular vacuum that isn't perfectly stable, it's conceivable that effects could arise that look like a violation of CPT symmetry from our limited perspective. Furthermore, some formulations involve background fields that permeate all of space, and these fields could interact with particles in a way that distinguishes between matter and antimatter in a manner not accounted for by the standard model, creating a potential crack in the mirror. Other speculative frameworks, like theories involving spacetime torsion or non-commutative geometry, where coordinates of spacetime themselves do not commute, meaning that measuring position in one order might give a different result than in another, also open the door to potential violations. These are highly theoretical ideas, but they share a common thread. They propose that at energies approaching the Planck scale or in environments as extreme as the singularity inside a black hole, the rules we take for granted might bend. The perfect symmetry of CPT, while an excellent approximation for our low-energy universe, could be revealed as an emergent property rather than an absolute law, much like how Newton's laws of motion emerge from the deeper reality of relativity. The tantalizing prospect of discovering such a violation drives physicists to design experiments of breathtaking sensitivity. These aren't searches for obvious breaks, they are hunts for deviations so minuscule they would be buried under layers of statistical uncertainty. Researchers look for any difference in the magnetic moments of particles and antiparticles beyond the already incredible precision we've achieved. They study the oscillation patterns of neutral mesons like kaons and B mesons with exquisite care, searching for a discrepancy between how a particle transforms and how its antiparticle does that cannot be explained by known CP violation alone, which would point directly to a T violation and thus a potential CPT break. They even look to the cosmos, studying the light from distant quasars to see if the properties of photons change over billions of years of travel, which could indicate a violation of Lorentz invariance that would challenge CPT's foundation. Finding even the smallest verified crack in the CPT mirror would be a revolution on par with the discovery of radioactivity or the expanding universe. It would be a direct signal of new physics, a message from a realm beyond our current theories, forcing a profound rewrite of our understanding of reality's most basic rules. For now, the mirror holds, but the search continues, driven by the thrilling possibility that the universe might still have profound and symmetry-shattering secrets left to reveal. This idea of a mirrored cosmos doesn't just exist in a vacuum. It has profound and startling consequences for our understanding of the universe's very origin. If a full CPT mirror of our reality is not just possible but mandated by the laws of physics, then we are forced to confront a monumental cosmological question: what was the true nature of the Big Bang? The event we perceive as the beginning of everything might have been something far more complex and symmetric than we ever imagined. Some of the most compelling theories in modern cosmology suggest that the Big Bang was not a single, isolated event that created only our universe. Instead, it may have been a moment of profound symmetry, giving birth to two universes simultaneously, the one we inhabit and its perfect CPT mirror. In this breathtaking scenario, the initial singularity didn't just expand into the cosmos we see. It bifurcated, creating a pair of twin universes that are inextricably linked yet forever separated by their fundamental properties. One universe, ours, was born with matter dominant, with a specific spatial handedness, and with time flowing in the direction we experience. The other was born as its exact CPT opposite, an antimatter-dominated, spatially mirrored universe where the arrow of time points in the reverse direction from our own. This elegant proposal offers a potentially revolutionary solution to one of the greatest unsolved mysteries in physics: the matter-antimatter asymmetry problem. Our best models of the Big Bang suggest it should have created perfect, equal amounts of matter and antimatter. These two opposing substances should have then immediately annihilated each other in a blinding flash of energy, leaving behind a universe filled with nothing but radiation, no stars, no planets, and certainly no us. But that's clearly not what happened. Our observable universe is almost entirely made of matter. For decades, physicists have searched for some mechanism, some violation of symmetry in the early universe that could have favored matter over antimatter by just 1 part in a billion, enough for a tiny surplus to survive the annihilation and form everything we see. The existence of a CPT mirror universe provides a beautifully simple and radical alternative. There was no asymmetry. The universe in its totality is perfectly balanced. All the missing antimatter isn't missing at all. It simply resides in the twin cosmos on the other side of the Big Bang. The annihilation was avoided because the matter and antimatter were separated at birth, placed into two distinct, evolving universes at the moment of creation. From the perspective of an observer in that mirror universe, their reality would be just as valid and consistent as ours. They would look out and see a cosmos made entirely of what we call antimatter, and they would perceive it as perfectly normal matter. They would trace their history back to a singular beginning, a Big Bang of their own, and they would have their own arrow of time pointing from their past to their future, which, from our external viewpoint, would be the exact reverse of our own timeline. This cosmic duality suggests a reality of breathtaking symmetry, where the Big Bang was less an explosion and more a process of differentiation, a moment where the perfect, symmetric potential of the initial state actualized into two complementary halves of a single, unimaginably vast whole. It challenges our very notion of a unique creation and hints that our entire existence might be just one half of a far grander, more balanced cosmological story. Yet this profound connection between a CPT mirror universe and our own origins inevitably pulls our gaze toward an even grander cosmic architecture, the multiverse. The idea of a single twin universe born from a symmetric Big Bang is captivating, but it may just be the first step into a far vaster and more varied reality. If the fundamental laws of physics allow for one perfectly mirrored cosmos, what's to stop nature from creating an entire ensemble of them? Multiverse theories, which posit that our universe is just one of countless others, provide a natural and expansive home for the concept of CPT-transformed realities. In such a framework, our universe and its antimatter, time-reversed twin wouldn't be a unique pair. They could be just one duo in an infinite cosmic crowd, a single reflection in a hall of mirrors stretching beyond comprehension. Within the landscape of modern multiverse ideas, the place of a CPT symmetric partner is particularly compelling. Take, for example, the inflationary multiverse theory, which suggests that the rapid expansion of spacetime during the Big Bang didn't just happen once but is an eternal process, continually spawning new, bubble universes with potentially different physical constants. In this endless froth of creation, it's entirely plausible that some of these budding universes would form not as independent entities, but as linked CPT pairs. Each bubble might inflate into a dualistic structure, birthing both a matter-dominated universe and its antimatter counterpart simultaneously, ensuring the overall conservation of symmetry across the multiverse at large. This elegantly extends the solution to the matter-antimatter problem from a single pair to a fundamental principle of cosmic creation. This line of thinking leads us to one of the most fascinating and speculative questions in all of physics. If such a partner universe exists, could there be any form of communication or exchange between it and our own? The barriers are, of course, monumental. Not only are these universes separated by what may be an unbridgeable metaphysical divide, but any attempted transfer of information would have to contend with the complete inversion of charge, parity, and time. A signal sent from our universe would, from the perspective of an observer in the mirror cosmos, appear to be traveling backward in time and be composed of antimatter. The very concepts of sending and receiving become philosophically tangled when the arrows of time are opposed. However, some theoretical models do allow for intriguing possibilities. The mathematics of certain quantum gravity approaches suggest that these twin universes might not be entirely disconnected. They could be linked through the deepest structure of spacetime itself, perhaps via the initial singularity of their shared Big Bang or through quantum entanglement operating on a truly cosmic scale. In such a scenario, an event in our universe might have a faint correlated echo in its partner, not as a conventional signal but as a fundamental, law-governed connection woven into the fabric of reality. While this falls far short of dialing up a parallel universe on a telephone, it hints that complete isolation may not be a guaranteed fact. Pondering this possibility forces us to reconsider the very nature of reality's structure. If a multiverse contains CPT partners, then the totality of existence is fundamentally symmetric and balanced in a way we can scarcely imagine. Every occurrence in our timeline, from the formation of a star to the thoughts in your mind, would have a corresponding time-reversed counterpart in another cosmos. This doesn't merely add more universes to a list, it creates a deeply interlinked and holistic cosmic whole where the distinctions between individual universes might be less absolute than they appear. Our perception of a unique, linear history could be just a single thread in a vastly more complex tapestry where past and future, cause and effect, matter and antimatter are all part of a symmetrical and breathtakingly beautiful greater picture. And this brings us to one of the most profound and dizzying questions raised by the entire concept. What would it actually feel like to live in such a universe? From our external vantage point, we would observe their reality as a grand cosmic film playing in reverse. We would witness planets unforming, stars drawing light and energy back into themselves, and civilizations aging backward from decay to birth. But crucially, for any conscious being within that cosmos, their experience would feel entirely normal and self-consistent. Their consciousness would be inextricably woven into the fabric of their local arrow of time. They would have memories of what we would call their future, and they would perceive their actions as influencing events yet to come, which for them would be their past. A scientist in that universe might conduct an experiment, see a result, and use that knowledge to form a hypothesis about the cause that, from our perspective, had already occurred. Their entire perception of causality would be flipped, yet it would feel just as logical and real to them as our own does to us. This forces us to confront the unsettling idea that the flow of time might not be an absolute feature of the universe, but rather a deeply personal and perspective-dependent phenomenon, a narrative constructed by a conscious mind to make sense of cause and effect within its own local timeline. This leads directly into a deep philosophical debate about the very essence of time. Is the direction of time, this thing we call the arrow, a fundamental property of the cosmos itself, or is it merely an emergent property of our conscious experience within it? One perspective, often called the theory of time, argues that the flow of time is real and absolute. In this view, there is a universal now that moves forward, and the past, present, and future have objective realities. If this is true, then a CPT-transformed universe would have its own absolute arrow, pointing in the opposite direction to ours. Its inhabitants would be living in what we consider the past, but for them it would be the present. The other major perspective, the B theory of time, suggests that all moments in time, past, present, and future, exist equally in a vast static block universe. The flow of time is an illusion of human consciousness, a way our brains navigate this eternal, unchanging structure. From this viewpoint, a CPT mirror universe isn't running backward at all. It is simply another part of the block, with its own set of events ordered from its own local perspective. In this model, the question of which way time really flows becomes meaningless. There is only the four-dimensional geometry of space-time and our conscious journey through it. The role of consciousness itself becomes paramount in this puzzle. Our brains are physical systems, and the process of forming memories is a thermodynamic event that increases entropy. We remember the past because our neural pathways are shaped by events that, from a physical standpoint, occurred in a state of lower entropy. In a reversed universe, a conscious being's brain would operate according to the local thermodynamic arrow. Their memories would be encoded of events that, from their perspective, happened in their past, which is our future. Their sense of free will, their experience of making a choice and seeing its consequence, would be just as vivid and real as ours. This suggests that the subjective experience of time's flow is not a direct perception of some cosmic clock, but is instead generated by the way our cognitive machinery interfaces with the thermodynamic gradient of our local environment. We are not passengers on a river of time, we are the river itself, and our consciousness is the current. Ultimately, the existence of a valid CPT symmetric universe challenges our instinctual belief that our experience of time is the only correct one. It proposes a profound relativity of temporal perspective. There is no privileged vantage point from which to declare that our timeline is forward and another is backward. Each universe, with its own consistent thermodynamic arrow and conscious observers, would experience its own unique and valid present moment. The laws of physics do not dictate a universal now, they only provide the stage. The play of consciousness, with its unshakable belief in a moving present, is performed locally within the confines of its own cosmic domain. This realization doesn't just expand our concept of the universe, it expands our understanding of our own place within it, suggesting that the relentless forward march of time we hold so dear might be a deeply personal story, not the universal truth we imagined it to be. But to truly understand the implications for a time-reversed cosmos, we must venture into the quantum realm where the rules become even more enigmatic. At first glance, quantum mechanics seems to uphold time symmetry beautifully. The cornerstone equation, the Schrödinger equation, which describes how a quantum system evolves, is perfectly time reversible. If you take its solution and mathematically substitute negative time, you get a perfectly valid state that the equation allows. This suggests that, just like a planet's orbit, the dance of an electron around a nucleus should look just as natural whether the film is run forward or backward. The fundamental evolution is symmetric. However, this pristine symmetry hits a monumental wall the moment we try to measure something. This is the infamous measurement problem. In the classic formulation of quantum mechanics, a particle exists in a fuzzy superposition of all possible states, like being in multiple places at once described by its wave function. But when we observe it, this wave function appears to irrevocably collapse into a single, definite state. We find the electron here and not there. This process of collapse is starkly time-asymmetric. We never see a definite, localized particle spontaneously explode back into a blurred cloud of possibilities throughout the room. The act of measurement seems to introduce a fundamental arrow of time that wasn't present in the smooth, reversible evolution of the wave function. This creates a deep tension. The underlying quantum law is symmetric, but our interaction with the system, the act of gaining knowledge, seems to break that symmetry. This has led to a fascinating spectrum of interpretations, each grappling with the problem of time in its own way. The Copenhagen interpretation, the traditional view, essentially accepts this asymmetry as a brute fact. The wave function collapses when observed, and that's that. In this view, the quantum arrow of time is tied to the act of consciousness or measurement itself, creating a puzzling chicken-and-egg scenario with the thermodynamic arrow. Other interpretations offer radically different perspectives. The many worlds interpretation provides a stunningly elegant solution. It proposes that wave function collapse is an illusion. There is no collapse. Instead, at the moment of measurement, the universe branches into multiple, non-communicating parallel worlds. In one branch, you see the electron here. In another, an alternate version of you sees it there. From this vantage point, the entire quantum evolution remains perfectly time-symmetric. The apparent randomness and irreversibility we see are because we, as observers, are trapped within a single branch of an ever-diverging cosmic tree. The flow of time is our journey along one specific branch. For a hypothetical observer outside the multiverse, the entire structure would be static and symmetric. Another compelling idea is the concept of quantum decoherence. This isn't an interpretation itself, but a process that explains why we perceive a collapse. It shows how a quantum system interacting with its environment, be it a few stray photons or air molecules, rapidly loses its quantum coherence. The information about its superposition leaks out into the environment, becoming effectively unrecoverable. This process is driven by an increase in entropy, creating a powerful and emergent quantum arrow of time that aligns perfectly with the thermodynamic one we already know. The irreversibility isn't in the laws, but in the practical impossibility of reversing these countless interactions with the environment. So what does this quantum quagmire mean for our CPT symmetric mirror universe? It reinforces the idea that the arrow of time is not dictated by the most fundamental laws, but emerges from specific conditions, whether they be the initial low entropy state of the Big Bang or the process of environmental decoherence. If the CPT theorem holds, then the quantum laws in the mirror universe must be identical. An observer there would witness quantum superpositions and what they would perceive as wave function collapse, all aligned with their local, reversed thermodynamic arrow. Their scientists would develop their own Copenhagen or many worlds interpretations, just as we have, completely consistent with their experience of time flowing from their past to their future. The profound takeaway is that the weirdness of quantum mechanics, with all its apparent paradoxes, might be just as reversible or irreversible as the classical world, depending entirely on the perspective from which you view the cosmic film. Yet for all the profound clarity that quantum field theory provides on flat spacetime, the story takes a dramatic and complex turn when we bring Einstein's general relativity into the picture. The serene, mathematical perfection of the CPT theorem rests upon the flat, unchanging stage of special relativity. But our universe isn't flat or static. It's a dynamic, curving, and expanding fabric. When we place our particles and symmetries onto this warped stage of curved spacetime, we are forced to ask if the most sacred symmetry of all can still hold its perfect form. At its heart, the equations of general relativity themselves possess a beautiful time symmetry. The Einstein field equations, which describe how matter and energy tell spacetime how to curve, do not care if you plug in a negative value for time. The mathematics works just as well whether the universe is expanding or contracting. A black hole forming from a collapsing star is a valid solution, and so is a white hole, its theoretical time-reversed counterpart, spewing matter outward. So in this pure classical sense, gravity itself seems to play by time-symmetric rules, but our actual universe clearly does not. We observe a cosmos that is expanding and has been since the Big Bang. This expansion introduces a powerful and irreversible arrow of time on a cosmic scale. If we were to somehow reverse the flow of time, we would not see a lawful, symmetric contraction. Instead, we would witness a universe behaving in a way that completely contradicts our observations. Galaxies would be moving toward each other, the background radiation of the cosmos would be heating up, and the universe would be heading toward a singular, high-density state. The expansion of the universe is a one-way process, and it defines a cosmological arrow of time that aligns with the thermodynamic one. This presents a fascinating puzzle. The underlying law is symmetric, but the specific solution that describes our reality, an expanding universe from a hot, dense state, is starkly asymmetric. The plot thickens even further when we consider the most extreme objects gravity can create, black holes. Black hole thermodynamics introduces another powerful and irreversible arrow of time. The famous second law of black hole mechanics, developed by Jacob Bekenstein and Stephen Hawking, states that the total area of all black hole event horizons in the universe can never decrease. It can only stay the same or increase, much like entropy. When matter falls into a black hole, its horizon area grows. When two black holes merge, the area of the new, larger black hole is greater than the sum of the areas of the original two. This is a one-way street. We never see a black hole spontaneously split into two smaller ones, just as we never see entropy decrease. Hawking radiation complicates this further, as it suggests black holes can slowly evaporate, but this process itself is incredibly slow and still involves an overall increase in entropy for the entire universe. The formation and evolution of black holes, therefore, stamp another irreversible direction onto the flow of time within our curved spacetime. This creates a profound tension for CPT symmetry in the context of a real gravitating universe. The CPT theorem, as proven by Pauli, relies on a flat and static spacetime background. But in a universe that is fundamentally dynamic and curved, can we even define a global CPT transformation in a consistent way? How do you perform a simultaneous reversal of charge, parity, and time across the entire expanding cosmos? This is not a simple question, and it remains an active and fierce frontier of research in theoretical physics. Some approaches suggest that to properly define CPT in a curved spacetime, we might need to consider the entire history of the universe from the Big Bang to its final state. Others have proposed that the presence of a cosmological horizon, the point beyond which we can never see due to the universe's accelerating expansion, might actually pose an ultimate challenge to CPT, potentially preventing it from being a well-defined symmetry for the cosmos as a whole. The quest to reconcile the flawless symmetry of the microscopic laws with the obvious arrows of time in our gravitating cosmos is one of the great journeys of modern science. It forces us to consider that the ultimate answer may lie not in choosing one over the other, but in discovering a deeper quantum theory of gravity where spacetime itself is not a static background but a dynamic, emergent property. In such a theory, perhaps the perfect mirror of CPT will find its most complete and elegant expression, not as a transformation on a fixed stage, but as a fundamental property of the cosmic dance between matter, energy, and spacetime itself. This deep connection between the unbreakable mirror of CPT symmetry and the fundamental concept of information takes us straight to the heart of one of the most heated debates in modern physics: the black hole information paradox. The principle of information conservation is a cornerstone of quantum mechanics. It states that information, the complete specification of the state of a system, can never be truly destroyed. It might be scrambled, diffused, or become practically impossible to retrieve, but in theory, it should always be preserved. If you knew the exact state of every particle in a burning log, you could, with godlike computational power, reverse the process and reconstruct the original log from the smoke and ashes. The information is never lost. This is where Stephen Hawking's famous calculation in the 1970s sent shockwaves through the physics community. He showed that black holes, through the quantum mechanical process that now bears his name, should slowly evaporate, radiating away their mass until they potentially vanish entirely. The problem is that this Hawking radiation is purely thermal. It's random noise carrying no information about what fell into the black hole. If a black hole evaporates completely, it seems all the information about the stars, planets, or books that were sucked in is irretrievably erased from our universe. This violation of quantum mechanics' most sacred principle created a paradox that has puzzled physicists for decades. Enter CPT symmetry. This profound principle suggests a breathtaking and elegant resolution. If CPT symmetry is absolute, then information must be preserved, full stop. It cannot be lost, even in the extreme gravity of a black hole. So if information seems to vanish from our universe, perhaps it hasn't been destroyed at all. Maybe it has been transferred. The perfect CPT mirror of our universe provides a potential repository for this seemingly lost data. In this radical view, the information swallowed by a black hole in our cosmos isn't annihilated. It is perfectly encoded and reflected into its CPT-transformed counterpart. From the perspective of an observer in that mirror universe, the event would appear as a white hole, a time-reversed black hole spitting out that very same information in a perfectly organized form. What looks like random, information-free Hawking radiation to us might be a coherent, information-rich signal from their point of view. This idea doesn't just preserve information, it preserves it in a beautifully symmetric way. The total information content of the entire dual universe system remains constant, satisfying the demands of quantum theory, while explaining why we, trapped in our single perspective, perceive a loss. It transforms the paradox from a problem of destruction into one of separation. The information is still there, just located in a part of reality we cannot access. This perspective is supported by the work of physicists like Don Page, who studied the information flow in black hole evaporation. His calculations showed that for information to be conserved, the radiation must eventually become highly correlated with the black hole's internal state. The CPT partner universe provides a natural mechanism for creating those ultimate correlations across a cosmic divide. This concept extends far beyond black holes to any process where information appears to be lost. Any event that seems to increase entropy and create irreversible disorder in our world could, from the grand, symmetric perspective of a CPT-transformed reality, be part of a balanced exchange. The cosmic ledger of information remains perfectly in check, with every bit of data created or altered in our timeline having its counterpart accounted for in the mirror. This suggests a universe that is not only deterministic in its laws but also utterly conservative in its narrative, ensuring that not a single detail of its history is ever truly forgotten, only viewed from a different angle in the vast tapestry of a fully symmetric cosmos. These cutting-edge experimental efforts are a testament to how seriously physics takes the principle of CPT symmetry, pushing our technology and ingenuity to the absolute limit in pursuit of the tiniest crack in the cosmic mirror. At the forefront of this hunt is the Alpha experiment at CERN, a marvel of precision engineering designed to answer a seemingly simple question with profound implications. Is an atom of antihydrogen truly identical to an atom of hydrogen? This is the most direct test imaginable. Antihydrogen is the antimatter counterpart to the most abundant and well-understood element in our universe, consisting of an antiproton and a positron. The alpha apparatus is a sophisticated trap that uses complex magnetic fields to capture and hold these elusive atoms, preventing them from instantly annihilating upon contact with ordinary matter. Once trapped, scientists can perform incredibly precise measurements, studying the light these atoms absorb and emit. The specific frequencies of this light, known as the atomic spectrum, are like a unique fingerprint for hydrogen. If antihydrogen has even a slightly different fingerprint, if its spectral lines are shifted by a minuscule amount, it would be a monumental discovery, a direct violation of CPT symmetry that would shake the foundations of modern physics. Simultaneously, another powerful line of inquiry focuses on the most ghostly and enigmatic particles we know, neutrinos and their antimatter counterparts, antineutrinos. These particles are notoriously difficult to study, barely interacting with other matter, which makes them perfect messengers from realms of physics we cannot yet directly probe. Experiments like T2K in Japan and NRV at Fermilab carefully fire beams of neutrinos and antineutrinos over long distances, watching as they oscillate, spontaneously changing from one type or flavor to another. The critical test is to see if neutrinos and antineutrinos oscillate at exactly the same rate. A difference in their oscillation probabilities would not just be another measurement, it would be a direct signal of a fundamental asymmetry, a hint that these particles and their antiparticles do not obey the same laws of physics. Such a finding could point toward a violation of CPT, as the symmetry demands their behavior be perfectly mirrored. These neutrino observatories are essentially ultra-sensitive cosmic tuning forks, listening for a dissonant note in the harmony of the universe. The pursuit doesn't stop there. Other experiments are searching for even subtler effects. Some are looking for minute differences in the magnetic properties of protons and antiprotons, while others are investigating the behavior of certain mesons, particles that are themselves a mix of quark and antiquark. The goal is always the same, to find any discrepancy, any deviation, no matter how small, between a property of a particle and the corresponding property of its antiparticle. The sensitivity required is almost beyond comprehension. These experiments are designed to detect differences of 1 part in a billion or even smaller. They are looking for a crack in a mirror that has so far proven to be flawless to an astonishing degree of precision. The motivation for this painstaking work is immense. Finding a violation of CPT symmetry would be far more than just winning a Nobel Prize. It would be a paradigm shift on the scale of the discovery of relativity or quantum mechanics itself. Because the CPT theorem is so deeply woven into the fabric of quantum field theory, a confirmed violation would force a complete rewrite of our most fundamental theories of reality. It would be the key that unlocks the door to a whole new world of physics that lies beyond our current standard model. It could provide the crucial clues needed to finally develop a theory of quantum gravity, unifying the world of the very small with the realm of space-time curvature. It might even help explain the universe's overwhelming preference for matter over antimatter, solving one of cosmology's greatest mysteries. Every measurement, every data point collected in these experiments is a step toward potentially glimpsing that deeper layer of cosmic truth, a reality where the most sacred symmetry is not quite as absolute as we once believed. This incredible possibility forces us to confront some of the most profound philosophical puzzles imaginable. If a consciousness were to emerge in that time-reversed cosmos, would it experience reality in a way we could even comprehend? Their stream of thought would be woven into the fabric of a universe where effect precedes cause. Imagine a being in that world making a decision. From our external viewpoint, we would see the consequence of that choice happen first, and then witness the being form the intention to make it. Yet for them, this would feel entirely natural. Their brain, a physical system operating according to the local thermodynamic arrow, would form memories of the events that, from their perspective, have already occurred. Their sense of free will, the feeling of making a choice that influences an open future, would be just as vivid and real as our own. The unsettling conclusion is that free will might not be tied to a universal direction of time at all, but rather to the internal, consistent narrative that a conscious mind constructs from the chain of events within its own local timeline. This completely inverts our most basic understanding of causality, the bedrock principle that cause must always come before effect. In our world, a billiard ball moves because it was struck by another. In the mirror universe, the sequence would appear reversed to us. A billiard ball would spontaneously leap into motion, and only afterward would we see another ball swing in to strike the place where it once was in perfect coordination. For an observer within that reality, however, the narrative would be perfectly coherent. They would perceive the striking ball as the cause and the motion as the effect. Their entire physical reality would be built upon this inverted causal framework, yet it would be just as logically consistent and law-governed as our own. This suggests that causality itself might not be a fundamental feature of the universe, but rather a perspective-dependent story we tell to make sense of the consistent correlations between events within our specific temporal reference frame. These ideas challenge the very core of our anthropocentric view of reality. We instinctively believe our experience of time, moving from a fixed past into an uncertain future, is the one true version. The existence of a valid CPT symmetric universe forces us to admit that our perspective is not privileged. There is no cosmic clock ticking forward for everyone. There is only local time, defined by the thermodynamic gradient of a given region of spacetime. This introduces a profound relativity of temporal experience. Your now and my now are the same because we share the same local arrow of time. But for a consciousness in the mirror universe, their now is completely different, yet just as real. This dismantles the idea of a universal present moment and suggests that past, present, and future might not be absolute states but rather relational properties, dependent entirely on one's location within the grand and symmetric structure of the cosmos. Ultimately, this isn't just a thought experiment about physics. It's a deep inquiry into the nature of existence and consciousness itself. It asks whether the flow of time is an illusion generated by our minds as they process information in a universe with increasing entropy. If that is the case, then a consciousness that emerged in a universe with decreasing entropy would generate the opposite illusion, a perception of time flowing just as relentlessly, but in the opposite direction. Both experiences would be valid interpretations of their local physical conditions. This leads us to a breathtaking and humbling possibility. That time, as we feel it, is not a river carrying us along, but a story we tell ourselves. We are not passive passengers on a journey from past to future. We are active participants, and the narrative of time is the language our consciousness uses to comprehend the beautiful, symmetric, and deeply mysterious universe we are a part of. String theory, our most ambitious attempt to weave gravity into the quantum tapestry, offers a fascinating and complex new stage upon which to examine the drama of CPT symmetry. This framework, which proposes that the fundamental constituents of reality are tiny, vibrating strings rather than point-like particles, naturally expands our conception of the cosmos to include extraspatial dimensions. Within this richer landscape, the meaning and enforcement of CPT take on entirely new dimensions of their own. Some formulations of string theory provide a remarkably natural and elegant home for this perfect symmetry, weaving it directly into the geometric fabric of the theory's mathematical structure. The very consistency of string theory often demands that certain symmetries, including CPT, be preserved, making it not just a feature but a foundational requirement for a stable, logical universe. However, the immense flexibility of the string theory landscape also opens doors to speculative scenarios where this sacred symmetry might not be absolute. The theory allows for a vast array of possible vacuum states, different underlying backgrounds or configurations for spacetime itself. In some of these possible universes, the vacuum might not be perfectly neutral. It could be permeated by background fields that interact differently with particles and antiparticles, or it could feature a fundamental granularity or foamy structure to spacetime at the smallest scales, potentially near the Planck length. In such exotic environments, the precise conditions that guarantee CPT conservation in our flat, four-dimensional perspective might subtly break down. This wouldn't be a dramatic shattering of the mirror, but perhaps a faint, almost imperceptible fogging, a slight preference that distinguishes matter from antimatter or gives a tiny nudge to the arrow of time. Perhaps the most profound contribution of string theory to this conversation is through its discovery of remarkable dualities. These are deep mathematical equivalences that show how two seemingly very different string theories, living in different numbers of dimensions or with different coupling strengths, can actually be two descriptions of the exact same underlying physics. The most famous of these is T-duality, which reveals that a string theory compactified on a circle of a certain radius is physically identical to a string theory compactified on a circle of the inverse radius. Then there is S-duality, which connects a world where strings interact weakly to a world where they interact strongly. These dualities suggest that our most basic concepts, like the size of a dimension or the strength of a force, might not be fundamental but instead relational and perspective dependent. This radically changes how we might view a CPT transformation. In a theory where the very nature of space and coupling constants can be fluid, what does it mean to mirror spatial coordinates or reverse time? A CPT transformation in one description of the universe might look like an entirely different, yet equivalent, operation in its dual description. It hints that CPT symmetry could be just one manifestation of a much deeper, more profound underlying symmetry that governs all of reality, a symmetry that unifies concepts we thought were separate and reveals a hidden unity in the laws of physics. String theory, therefore, doesn't just test CPT symmetry, it elevates it, suggesting that our perfect cosmic mirror might be merely a reflection of a far more magnificent and interconnected geometric truth waiting to be discovered. Now, this absolute requirement of CPT conservation presents us with a fascinating and crucial puzzle, because we know for a fact that one of its component parts is not always preserved. While the combined trio of charge, parity, and time reversal is sacred, the duo of charge and parity together, what we call CP symmetry, is actually violated in nature. This isn't a theoretical maybe, it's an observed fact that plays a starring role in the very existence of our material universe. The discovery of CP violation was a monumental shock to physics, and understanding how it fits with the unbreakable rule of CPT is key to seeing the bigger, more beautiful picture of cosmic symmetry. Let's break down what CP violation means on its own. A CP transformation takes a particle and turns it into its antiparticle while also mirroring its spatial coordinates. For a long time, physicists believed this combined operation would always leave the laws of physics unchanged. But in 1964, James Cronin and Val Fitch made an astounding discovery while studying neutral kaons, certain exotic subatomic particles. They found that the rate at which a kaon decayed was ever so slightly different from the rate at which its antimatter counterpart decayed. This tiny difference was a direct violation of CP symmetry. It meant that the universe, on a fundamental level, treats a process involving matter slightly differently than the exact mirror image process involving antimatter. It has a tiny built-in bias. This minuscule bias is not just a curious footnote, it is the leading candidate for solving one of cosmology's greatest mysteries. Why are we here? The Big Bang should have created exactly equal amounts of matter and antimatter, which would have then immediately annihilated each other in a spectacular burst of pure energy, leaving behind a vast, empty, and boring universe. The fact that we have a universe filled with galaxies, stars, planets, and people means that somehow, for every billion particles of antimatter created, there must have been 1,000,000,001 particles of matter. That 1 part in a billion surplus is all that survived to build everything we see. CP violation provides a mechanism for this. In the extreme heat of the early universe, processes governed by the weak nuclear force that involved this slight asymmetry could have preferentially decayed, producing just that tiny bit more matter than antimatter, giving our universe its material foundation. So how does this CP violation, this broken symmetry, coexist with the absolute requirement of perfect CPT symmetry? The answer is both elegant and profound. The CPT theorem essentially tells us that the universe's lawbook is perfectly balanced, but only when you consider the complete picture. If CP symmetry is violated, then for the overall books to remain balanced, time reversal symmetry must also be violated to exactly the same degree. The imperfections cancel each other out. Think of it like a set of cosmic scales. On one side, you have the known violation of CP. To keep the scales perfectly level, as demanded by the unbreakable CPT theorem, the other side must have an equal and opposite violation of T, time reversal symmetry. The universe's fundamental loyalty is to the combined trio, not to any of the individual parts. This forces a stunning conclusion. The same experimental discovery that proved CP violation also provides indirect but powerful evidence for a fundamental violation of time reversal symmetry at the microscopic level. The slight difference in how a kaon and an anti-kaon decay doesn't just mean the universe distinguishes between matter and antimatter in a mirror. It means the fundamental laws of physics themselves can tell the difference between forward and backward time. This isn't about entropy or thermodynamics. It's a built-in arrow of time written into the quantum mechanical rules governing particle interactions. The fact that we live in a universe where cause precedes effect isn't just a statistical accident. It's woven into the very fabric of the forces that shape reality, a direct consequence of this subtle, foundational breaking of time symmetry that perfectly counterbalances the breaking of CP. The second law of thermodynamics is often what we point to when we try to explain why time feels so one way in our world. It states that entropy, a measure of disorder, always increases in an isolated system. This gives us the thermodynamic arrow of time, the reason we see smoke disperse but never gather back into the cigarette, or why we remember the past but not the future. Our universe seems to be on a relentless march from order to disorder. But if we take the idea of a CPT symmetric universe seriously, we have to ask a truly mind-bending question. In a cosmos where time itself flows in the opposite direction, what would happen to entropy? Would it magically decrease, defying everything we think we know? Or would the experience of time and entropy be somehow locked together, creating a consistent reality for any observer, no matter which way their timeline points? Let's start with the simplest, most intuitive assumption. If we could somehow peek into this mirror universe from our external perspective, watching their reality like a film playing in reverse, we would indeed witness what would appear to us as entropy decreasing. We would see shattered vases rise from the floor and reassemble themselves on tables. We would observe vast clouds of cosmic dust gracefully coalesce into brilliant stars and structured galaxies. The entire universe would seem to be moving from a state of chaos to a state of perfect order, like a movie of our universe playing backward. From our vantage point, it would look as if the second law of thermodynamics is completely inverted. However, this is where our intuition, based on our external view, leads us astray. The true, profound insight is that for any conscious being actually living within that universe, their experience would be completely different and entirely self-consistent. Their consciousness, their biology, and their very process of forming memories would all be inextricably linked to the local thermodynamic arrow of their own environment. In their reality, entropy would still be increasing. They would perceive their past as a state of lower entropy and their future as a state of higher entropy, just as we do. A spilled drink, from their perspective, would be a normal event where liquid spreads out and becomes more disordered. They would never see that liquid spontaneously gather itself back into the glass, because that would represent a decrease in entropy from their point of view, an event as statistically miraculous and forbidden for them as it is for us. This resolves the apparent paradox by revealing that the arrow of time is not an absolute property of the cosmos but a relative one, deeply tied to the local perspective of an observer. The second law of thermodynamics doesn't say that entropy must increase in some universal, God's eye view. It says that entropy increases in the direction of the thermodynamic arrow that defines the local flow of time. In our universe, that arrow points in the direction we call forward. In the CPT mirror universe, that arrow points in the opposite spatial and temporal direction, but it is just as real and just as governing for its inhabitants. Their forward is our backward, and their increasing entropy is our decreasing entropy, depending entirely on which side of the mirror you are standing on. This means the inhabitants of that reversed cosmos would develop the exact same scientific laws we have. They would discover the second law of thermodynamics through their own observations and experiments. They would see ice melting in a warm room, never freezing spontaneously. They would watch ink diffuse in water, never concentrating itself. They would have a past they remember and a future they cannot see, and they would explain it all with the same elegant concept of ever-increasing entropy. Their physics textbooks would contain the same equations, describing a universe evolving from a state of low entropy to high entropy. They would be just as puzzled as we are about why their universe began in such an exquisitely ordered state, completely unaware that from our external perspective, their Big Bang is what we would call the far, far future. This incredible relativity of perspective forces us to accept that our experience of time's flow is not a discovery of a fundamental cosmic truth, but a story written by our consciousness as it navigates the local thermodynamic conditions of our particular corner of reality. The quest to test the ultimate limits of CPT symmetry is far from over. In fact, it's accelerating into a new era of unprecedented experimental precision. Scientists are designing next-generation tools that will probe this fundamental principle with a sensitivity that was once the realm of pure science fiction. These aren't just incremental upgrades, they are monumental leaps in technology that will allow us to stare even deeper into the cosmic mirror, searching for the faintest possible crack that could reveal an entirely new layer of physics beyond our current understanding. At the forefront of this effort are plans for future particle colliders of staggering power and complexity. Projects like the Future Circular Collider, a proposed 90-kilometer ring that would dwarf the Large Hadron Collider, aim to smash particles together at energies we've never before achieved on Earth. By creating these extreme conditions, physicists hope to produce and study exotic particles and their antiparticles in vast numbers, watching for any minuscule deviation in their behavior, their decay rates, or their properties. These high-energy environments are like cosmic microscopes, allowing us to peer into the fundamental laws at a resolution so fine that even a violation 1 part in a quadrillion could be detected. It's in these fiery collisions that we might finally catch a glimpse of physics that operates outside the perfect symmetry of our current models. Alongside these colossal machines, a parallel revolution is taking place in the realm of antimatter research. Laboratories like CERN are developing new generations of traps that are colder, more stable, and more sensitive than anything that exists today. The goal is to create and hold atoms of antihydrogen for weeks or even months, not just minutes. With this kind of extended observation time, scientists can perform spectroscopic measurements of unimaginable accuracy, comparing the light absorbed and emitted by antimatter to that of ordinary matter with a precision approaching 1 part in a quintillion. They will also subject these anti-atoms to the pull of gravity with experiments like for example, IS and G-bar, watching with bated breath to see if an anti-atom falls downward like normal matter, or if it exhibits any behavior that would shatter our expectations and violate the equivalence principle, a cornerstone of general relativity that is intimately linked to CPT conservation. But the laboratory is not the only place to look for answers. The cosmos itself serves as a grand, natural experiment that has been running for over 13 billion years. Astronomers are now using powerful new telescopes and observatories to scan the heavens for any evidence of CPT violation written into the fabric of the universe. By studying the light from the most distant quasars, which has traveled across billions of light years to reach us, they can search for tiny changes in the properties of photons or fundamental constants over cosmic time. Any such variation could be a sign that the laws of physics are not perfectly immutable, and that symmetries we hold sacred might slowly evolve or break down on the largest scales. Furthermore, the ongoing mystery of dark matter and dark energy presents another avenue for discovery. If these enigmatic components of the universe interact with matter and antimatter differently, it could provide an indirect pathway to observing a cosmic-scale breakdown of CPT, a flaw in the mirror that has shaped the entire evolution of the cosmos. The implications of these future experiments are nothing short of revolutionary. Finding even the slightest, most confirmed violation of CPT symmetry would be a seismic event in physics, forcing a complete rewrite of the standard model and our understanding of quantum field theory. It would be our first direct clue to the nature of the deeper reality that must lie beyond, potentially offering a path to finally unifying gravity with quantum mechanics. Conversely, if all these next-generation experiments only serve to confirm CPT symmetry to ever more exacting degrees, that too is a profound result. It would elevate this principle from a well-tested theorem to something approaching an absolute metaphysical truth about the structure of reality, reinforcing the breathtaking idea that our universe is but one half of a perfectly balanced cosmic whole. Either outcome leads us closer to answering the ultimate questions about time, antimatter, and the very nature of existence. This journey into the deepest layers of reality brings us to the ultimate proving ground for CPT symmetry, the quest for a theory of quantum gravity. Our most successful theories, quantum field theory and general relativity, operate brilliantly in their own domains, but they speak different languages when it comes to describing the universe's most extreme environments, like the singularity at the heart of a black hole or the very first moments of the Big Bang. Reconciling these two pillars of physics is the single greatest challenge in theoretical physics, and how CPT symmetry survives this merger is one of its most severe tests. The smooth, continuous spacetime that the CPT theorem relies upon might simply break down at the unimaginably tiny Planck scale, where the quantum foam of reality churns and spacetime itself may become discrete or possess a fundamental graininess. In this realm, the very concept of a simultaneous charge, parity, and time reversal across the entire cosmos might not even be well defined, threatening the absolute nature of this most sacred symmetry. Different approaches to quantum gravity offer wildly different predictions for the fate of CPT. Take loop quantum gravity, for instance. This framework proposes that space is not smooth and continuous, but is instead woven from a network of tiny, discrete loops. In this pixelated view of spacetime, there is a natural minimum scale, which could potentially introduce a preferred direction or frame of reference. If such a fundamental reference frame exists, it could provide an anchor that allows for a subtle violation of Lorentz invariance, the very principle that underpins the CPT theorem. A universe with a built-in preferred direction could treat matter and antimatter, or forward and backward time, in slightly different ways, creating a tiny but measurable crack in the cosmic mirror. Then there's the fascinating approach of causal dynamical triangulation. This theory models spacetime as being built from incredibly small, fundamental building blocks, tiny triangular pieces that snap together to form the fabric of the cosmos. This method doesn't assume smoothness from the start. It lets the geometry of spacetime emerge from the way these pieces connect. In simulations using this model, researchers have found that a four-dimensional classical universe like our own can indeed emerge from this chaotic quantum bottom layer. But the question remains, does the CPT symmetry we observe and rely upon also emerge perfectly intact from this deeper, more fundamental description? Or does it only appear absolute from our large-scale, low-energy perspective, while potentially being only approximate at the Planck scale? This is an active area of research, with some models suggesting that the extreme conditions near a black hole singularity or the Big Bang could allow for CPT-violating processes that are otherwise completely forbidden in our calm, present-day universe. The stakes for this investigation couldn't be higher. Finding any violation of CPT, even one confined to the realm of quantum gravity, would be a revolutionary discovery. It would be a direct signal from a realm of physics beyond our current theories, offering crucial clues for how to finally build a complete theory of quantum gravity. It could help explain the initial conditions of the universe, perhaps providing a mechanism for why the Big Bang started in a state of such phenomenally low entropy. Conversely, if CPT symmetry holds firm even when gravity is fully quantized, it would elevate this principle from a powerful theorem to something approaching a metaphysical necessity, a non-negotiable feature of any coherent description of reality. The ultimate fate of CPT in the quantum gravity era will reveal profound connections not just between matter and antimatter, but between the quantum world, the gravitational force, and the very origin and nature of time itself. Indeed, the journey through the mind-bending landscape of CPT symmetry reveals one of the most profound and fascinating possibilities in all of science, the idea that a true mirror universe could exist, a cosmos where time flows in the opposite direction and antimatter forms the very substance of reality. While this concept stretches the limits of our imagination, it is not mere science fiction. It is a possibility firmly grounded in the rigorous, well-established principles of quantum field theory, a framework that has passed every experimental test we have thrown at it with flying colors. This isn't wild speculation, but a logical extension of our most trusted understanding of how the universe operates at its most fundamental level. The ongoing, meticulous search for any violation of this perfect symmetry is far more than an academic exercise. It is a powerful engine driving experimental physics into bold new territories. Every time scientists at facilities like CERN trap an atom of antihydrogen for further study, or when neutrino observatories analyze the subtle dance between particles and antiparticles, they are conducting a profound test of reality's deepest rules. They are peering into the cosmic mirror, polishing it to an ever higher degree of precision, searching for the tiniest crack that would signal a revolution. Finding even the most minute deviation would be a seismic event, forcing a complete rewrite of the standard model and potentially unlocking the door to a unified theory of quantum gravity, finally merging the world of the very small with the realm of spacetime and curvature. Ultimately, this exploration forces us to confront the very nature of existence itself. It challenges our anthropocentric view that our experience of time flowing irrevocably from past to future is the one true version. The profound relativity suggested by CPT symmetry humbles us, proposing that our present moment, our arrow of time, and our very consciousness are not absolute features of the cosmos, but are instead deeply personal narratives, shaped by the local thermodynamic conditions of our particular universe. Whether we ultimately discover a twin cosmos or simply continue to confirm the unbreakable nature of the mirror, this journey expands our understanding of reality, hinting that we may be part of a far grander, more balanced, and breathtakingly symmetric multiverse than we ever dared to dream.